Hey, everybody. This is Astronomy Daily Live. Nice to see everybody out there. Hope everybody's doing well. I'm going to do my usual thing and get off of that. Otherwise, my machine will freeze. All right, so I'm fixing that. Fixing that. Coming over to the chat. Hey there, Tom. Nice to see you in the chat. So, cheers. Hope hope everybody's doing well out there. Atta, nice to see you. Thanks for coming in again. So gather around, friends. Let's uh let's think and talk astronomy for a while. Just for a little while. Who knows? Sometimes sometimes it's an hour, sometimes it's a little more, sometimes it's a little less. Usually a little bit more. So I get uh I get going and yeah, it's like momentum. Yeah. So yeah, all is well here. Sort of took another lazy day. Uh, was was gonna go into work, but decided I really didn't have to. So it's like, well, then I ain't. I ain't. But tomorrow we'll be back to pretty much normal. So I will enjoy it. I will enjoy it while it lasts. So cheers. That's cool, Atem. Yeah. Well, find out, you know, when and where their meetings are, and go to one and you know, see what happens. See what happens. You know, hopefully, hopefully, you know, you'll sort of get a good vibe and uh, you'll like it. Uh, Pretty much as soon as you sort of walk into that space and if you do, then I'd say you've got a good match. So you know, pursue that for sure. So yeah, that'll help a lot. That'll help a lot because people in the amateur area um, uh, can be pretty rabid, pretty rabid. Now, I gotta say that ham radio operators are probably more rabid, but amateur astronomers, they're sort of right behind the um, the hams uh, in just you know, insanity and a lot of passion, a lot, and that's you know, having an amateur passion is is really cool. Is really cool. So yeah, go for it. They, as I said, you know, hopefully they'll be uh, friendly and open and you know, everything you need to sort of, you know, slip in and yeah, you know, I mean, if nothing else, you know, if you don't get involved in any other way, go to the meetings, and you know, oftentimes, you know, they'll have some kind of newsletter or some kind of deal that you can get, like um, some kind of a subscription to a magazine like um, uh, like Astronomy magazine or Sky and Telescope. Sometimes sometimes they'll offer you deals on that. You know, if you're a member. So yeah, yeah, and go to at least a couple. You know, one one I think is probably enough to get a good assessment, because once you've seen one, that's pretty much what they're like. Um, but go to at least one star party, and check out check out the action there, because that's a lot of what amateurs do is they party under the stars, and bring their scopes out, and have a good time. Just looking around, and chit chatting, and you know being cold and tired at the same time, and you know everybody is in that situation. So it's a little, and it's dark, right? So it's yeah, it's a different kind of environment, um, uh, but kind of neat, especially when you get to look through a bunch of scopes, and evaluate uh, how how uh, uh, how you like those things, right? I'm just reading your comment there, Ata. Yeah, 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 yeah. It's a passion is a sure uh, signature of life. Yeah, I would definitely say. So without that, there's not much more. Not much more. So cool, cool. Well, I'm glad you're finding your way through the maze, and it's not that bad. Have fun, enjoy, and if it turns out that it's something that you know you're you're not really into, find what you are. You know, that's all. But I think astronomy is cool, and it can be approached at many levels, right? So I mean, if you never get into astrophotography, or even into research or anything else, so what? Going outside, looking around, going wow, that's what it's all about. And that can be approached at any level, and is, right. The professionals have a um, certain appreciation where they're going wow, right. And that's different, slightly different than what the amateurs would perceive as wow, right. And it's definitely what a beginner, uh, yeah, that would be almost completely different from what a beginner considers wow. So things change, right? And I like it. Cheers. So yeah, once again, I don't really have any topics planned. I was going through archive, which is why I was actually a little bit, just just a little bit late on this live stream. I think I was almost 2 minutes late, almost. So that's becoming sort of a crisis when it's 2 minutes. It's like, whoa, there must be something really wrong. No, no, I was running a little bit slow because I was looking at the archive stuff, um, trying to see if there was anything interesting over there, and so let's go over and take a look at that. So I'm gonna share my screen, and while we go to infinity, I'm gonna start up my smartphone and get on this live stream. Good morning, Space TV. Hope all is well over there. Thanks for stopping in. Yeah, it looks like we're running. Just going to go over to archive and see. I like to sort of follow my nose on things. You know, don't really worry too much uh, about much of anything. Um, it's sort of like like a Bob Ross painting, right? He he was very sort of unconcerned because his technique sort of uh, uh, moved the final paintings to a destination, and so that's sort of the same thing I'm doing here. We're just going along, and you know using this technique of exploration, um, and uh, curiosity, right? And just sort of see what's up, right? GMO free. Yeah, 3 days until asteroid day. Very cool. So let's look at the new ones here. This is the latest and greatest in astronomical research. And it's both, theoretical, observational, combination of those two. Um, they're scientists and astronomers, of course, are included in that. They spend a substantial amount of time with their models, right? With their mathematical models that they have encoded inside of computer software, and they have access to a number of different parameters. So they can change those if they want to or need to, and then they can dial up like a recipe of some sort, a little bit of this, a little bit of that, um, and then press the go button, and see what happens on you know uh, whatever time scale they're interested in, right? They can go nanoseconds, uh, or they can go billions and trillions of years. uh, so yeah, that's the power of the model, is that it uh, it allows you to it allows you to, well, one, it's a feedback, right? So if if you develop some kind of a model and it matches your observations based on the parameters that you gave it, then you know that's a feedback thing saying, well, you know this model matches the data to this kind of accuracy and precision, and you can sort of decide from there whether that's acceptable or not. So yeah, models are great, and it's you know uh, you spend half your time. Well, actually, I would say you spend about 3/4 of your time battling code, right? Computer programming. You spend 3/4 of your time doing that, and 1/4 of your time actually working on the mathematics. Make sure that you're right. Uh, uh, Run it through various mathematical tests, whatever, right? But yeah, most of your time when you're working on a model, you're you're fighting code. You're finding bugs in the code that you have to identify and correct, and it turns into a project, right? But once you think you've got a pretty strong model, then you can start using it, to predict what might happen in the future and what might happen in the past. And given, certain uh, conditions at a certain time, what should it look like now, given what we understand about it? Those kinds of things. Very, very cool stuff. But that's what a lot of these papers are. And as I said, combinations of observation and theory. And these papers just take a massive amount of effort. Every single one of them. I've got incredible respect for anyone who you know bothers to write down you know what they're doing and what the results were and how they interpret the results and what problem are they trying to solve and all of that. And to take the time and effort to do that is awesome. But that's the process of science, right? Scientists don't they want to tell everybody. An excess of Jupiter analogs in super Earth systems. Hmm. Finding too many Jupiters, they think. Thought I saw a couple in here that looked moderately interesting. The variable wavelength dependent of the dipping event in KIC 8462852. A dipping event. And variable wavelength dependent. So, there was some kind of a dipping event, which I guess is a dimming event, right? KIC undergoes an unexplained dimming events or dips on the timescale of days. Uh, let's follow our nose here. See what turns up on the timescale of days, which were again observed from the ground from May to December 2017. Uh, Monitored with multi-band photometry by the Las Cumbres Observatory, all four dips um, display clear wavelength dependence. So, yeah, the time and the structure of each of the dip is different depending on what wavelength you look at it. So, we measure how the wavelength dependence changes over the whole dimming event, including the dimming between the dips and the brightening event. The blip, which occurs after the dips. We find that a single wavelength dependence does not fit the entire light curve, and the dimming occurring between the dips is non-gray and varies in time. Because of the non-gray dimming between the dips, we measure the wavelength dependence of the dips separately and without the extra depth from this dimming. Such measurements yield a different estimate of the wavelength dependence uh, of the dips, but remains consistent with the previous measurement, except for the first dip, which is surrounded by dimming with strong wavelength dependence. We find, yeah, wow, they're just finding all kinds of interesting structures in these dips. Shall we take a look at that? Now, when we look at objects at different wavelengths, what we're essentially doing is looking at different stuff, right? We're looking at different material uh, in and on the object that we're observing. So in this case, we're looking at a star, right? And so depending on the wavelength and the bandwidth, um, you know, uh, we're only going to be looking at, uh, some of the stuff. The rest of the stuff will be um, either completely invisible or completely black, completely opaque. And there's a little bit of grayscale in between that. Um, so 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 yeah, you just have to yeah. So let's see. Um, let's take a look and see. Uh, I always I always like to go to the pictures first. So an otherwise typical F main sequence star. Uh, this star displayed a series of large decreases in observed flux, up to 20% during the Kepler mission. Uh, the dips were asymmetric, and the Kepler light curve showed little evidence of periodicity in these events, although later observations and analysis showed hints. Is this Tabby Star? We're talking about Tabby Star. Isn't that the one that was dimming, that had dimmed by 16% over the last century? Isn't that the same one? Hmm. Yeah, I think this is. That's right. Okay. Well, let's look at it anyway, even though it's a more popular thing. But yeah, I think this is I think this is Tabby Star. If I remember right. Anybody check me on that? We can look at the name. Let's Google that name. Whoop. Uh-oh. Uncle Bill, nice to see you. I'm just trying to remember if this is Tabby Star or not. Maybe I'm thinking of a different one. Yeah, yeah, it is Tabby Star. There we go. That is Tabby Star. All right. All right. Well, I've got to get my Linux screen back up here and running. All right. Well, let's take a look anyway, huh? Since we're here. So I guess they named these dips. They named the dips. And yeah, they're different at different wavelengths for sure. At least the depth of the dip is different. The the shapes, you know, harder to tell here, but maybe we'll get some zoom ins. Wavelength dependence over time. Dip ratios. Yeah, so wow, they're finding like 3 to 1. Pretty well, yeah, I don't know. I don't know if that's pretty consistent or not. It's hard to tell. I gotta understand what those numbers mean a little bit more. I think it's just the ratio. Yeah, the ratio of the depths. Oh, okay. Okay. I'm not quite sure what the second one is. If that's just another epoch. So pretty interesting. It's hard to hard to understand why there would be a wavelength dependence on these dips. That's a that's a that's a tough that's a toughie. It's a long paper. So the variable wavelength dependence observed in the light curve suggests that the dusty material occulting Tabby Star is heterogeneous in size, composition, or both, but small changes in these properties can result in large changes in wavelength dependence. The opacity of a dust grain is very sensitive to the grain size in the submicron range for visible light. So, despite that dip ratio being much larger for Celeste, um, the grain size is only a factor of less than approximately 2, uh, smaller than the other 3 dips. The depth ratios can be even more sensitive to the composition. For example, a zero point 0.2 micron size grain is consistent with Celeste if ice. Huh, okay. I have a hard time reading that sentence. That's a weird sentence. Dust is highly unlikely to be homogeneous in composition, so small changes in relative proportions could explain the variation in wavelength dependence as well as size fluctuations. So I don't know. Kind of interesting. Suggesting variations in the properties of the dust. Since the dips and secular dimming occur together, the reference point for normalizing the light curve is important when measuring the wavelength dependence of the dips. Okay. Got any more pictures? A few more pictures. Not sure how to really read these pictures. Not quite sure what they're supposed to be depicting. So that's sort of a bummer. It's yeah, I don't really know how to read those. There's another one. Whole bunch of them back here. And I can't. I would have to. I would have to probably read the paper several times in order to understand what these last figures. But maybe it's something simple. So as I said, we're going along this together. So let's look for corner plots. So corner plot for the Elise fit with the normalization in the B band. And I don't know. I'm not seeing it. I'm not and yeah, I'm not going to waste anybody's time me trying to figure these things out live. This is something I can do offline, but I've seen these a couple of times now, and I I I'm not quite understanding what I'm seeing. I mean, there's some kind of histogram, like a 2D histogram, but yeah, I don't know how to read it. I don't know how to interpret those things. All right, well let's go back and see if there's anything else interesting here. Oh, a little too far. Start us at the beginning again. I don't think we were too far in it. Come on. Yeah, there it is. I did find this one paper down here pretty interesting. I think it's towards the end. See if I can see it. First, for the first polluted white dwarf from Gaia Data Release 2, the cool DAZ white dwarf star Gaia J 1738 minus 0826. See, so you see, I don't have a problem with these kinds of names because that's probably a right ascension and that's probably a declination. So it tells me where it is. And yeah, I think that's a nice thing to know. Metal polluted single white dwarf star identified through Gaia Data Release 2. Selected from color and absolute magnitude cuts in the Gaia Data Release 2 data, was discovered to have strong calcium 2 absorption in initial spectroscopic characterization at LIC. And it resembles in many ways the first confirmed metal polluted hydrogen atmosphere white dwarf. So kind of interesting. Don't know don't know how that can happen, right? Don't know how these weird things are happening. Can't explain them. That's a pretty weird one. Let's see, where is that? The remnant radio galaxy associated with NGC 1534. There was a really interesting, and as I said, it was towards the end here. Yeah, I think this was it. Visibility service for observing nights. So they've come up with a piece of software to schedule observations more efficiently, apparently. So I can appreciate that. Let's take a look here. See what these French astronomers have to say about these things. So preparation of detailed night schedule prior to an observing run can be tedious, especially for solar system objects, which coordinates are epoch dependent. We aim at providing the community with a web service compliant with virtual observatory standards to create tables of observing conditions together with air mass and sky charts for an arbitrary list of targets. So they take advantage of available VO services such as Simbad, Aladdin. I have never heard of this Myriad ephemerides generator to build a new service dedicated to the planning of observations. Requests for ephemerides charts and tables are handled by a VO compliant web service. For each date and each target, coordinates in local and equatorial frames are computed and used to select targets accordingly to users' criteria for visibility. So they're calling it Vision, Visibility Service for Observing Night. It allows anyone to create graphics of observing conditions and tables summarizing them. So this is very cool. To prepare and conduct observations from the ground-based telescope, many astronomers create Airmass charts, also called visibility plots. These graphics represent the elevation above the horizon or altitude of each target during the night, providing a graphical and easy way to schedule the sequence of observations. Yeah, when you're doing most kinds of photometric work, you definitely need to plan where you're going to be making your observation, where that object is going to be in the sky, because depending on how high above the horizon it is, there's going to be a certain amount of atmospheric refraction, which is going to uh, it's going to well, if you're looking at color data, it's going to mess up your colors. So you have to have a way of measuring that refraction and countering it. It's really easy. It's something that's done in the data reduction process, because that's a systematic thing that isn't part of the object that you're observing. So you want to be able to take it out, and we can do that. Refraction is a known quantity. We can know exactly how much uh, of the light is being refracted, depending on where the object is in the sky. That's just a mathematical model, and it works. Works really well. So let's see what they've got here. Yeah, this is just okay. So here's so this is their description of the algorithm. So for each requested date, a series of computations are performed prior to selection of targets suitable for observation. So first, the ephemerides. Ephemerides are just uh, the positions of these objects, usually right ascension and declination, um, over a certain period of time. So, like you might generate um, an ephemeris for the motion of Mars. Um, and that list can show the position of Mars like every minute or every hour or every day or every year, um, whatever you prefer, every second, every hundredth of a second. Um, uh, yeah, so that's what an ephemeris is. Um, Ephemerides is just the plural of um, ephemeris. It's one of those weird English things. Don't know where that came from. My apologies. um, so first, the ephemerides of the sun are computed to determine the instance of sunset and sunrise, the limits of the civil, nautical, and astronomical twilights corresponding to the times when the altitude of the sun is 6, 12, and 18 degrees below the horizon are also computed at this stage. Second, the phase and position of the moon throughout the night is computed and stored. Finally, the topocentric um, astrometric coordinates of each target are computed with a time step of 5 minutes and expressed as equatorial, right ascension, declination, um, horizontal, azimuth and altitude, and galactic coordinates. And that's that's gamma and beta, right? Is that right? Or is that lambda and beta? I think that's lambda and beta. So additionally, both solar and lunar elongations are computed at each time step, together with the solar phase angle, the heliocentric distance and range to the observer. These detailed coordinates are used to determine for how long each target is visible during the night. The entire list of criteria um, defining observability is provided in section 4. Okay, well, cool. So, you know what? Um, I gotta say that there's I don't really know what they're doing new here. Um, uh, because these kinds of I don't know if these well maybe these kinds of things just aren't available. But I mean, when I had to do this, because I was involved in a project doing photometry of white dwarf stars, and I wanted to know uh, when the best time to make these observations was, and of course it depends on where in the sky these objects are. Um, Usually, you want them as high in the sky as you can get. So with us in the northern hemisphere, that means, and actually in both hemispheres, the highest the object is going to be above the horizon is when it crosses the meridian. Now, the meridian is a line that goes from the North Pole through the zenith and down to the South Pole. That is your local meridian. And when a star intersects that line, moving from east to west, of course, when a star or an object intersects that line, that will be their highest altitude above the horizon. And that's sort of what this plot is showing, right? Is that, at different times, certain targets will be at their optimal height, at their highest height at a particular time. And it depends on where in the sky they are. That's all. So, yeah, I mean, I think this is pretty easy to do. So I'm not quite sure what they're making any better, because this is all sort of, I mean, this is all pretty basic. So they can select various criteria. Well, that's okay. Guess what this thing does is it also schedules it, right? It schedules it. It not only, just makes these little plots so you can sort of see it. It schedules observations. So that's pretty cool. Allows anyone to create graphics and data tables for observing conditions of solar system. Oh, okay. Well, no, it doesn't. It doesn't actually create a schedule. Oh, yeah. Okay. Well, I'm sort of back to, well, I don't know, because these kinds of things, this is pretty easy, really. So, yeah, I don't know. I mean, it's cool that they did it, and it's great that it's open source. But yeah, every observer has to do this. So yeah. But maybe these kinds of services just aren't available online, and and maybe they noticed that where nobody else did, and it's like, okay, well, let's put one online, right? Or make it available online at least. So that's cool. That's cool, but not too impressed. Not too impressed. I think that was I think that was about it. Always pretty amazing work here. You know, as I say over and over again with these papers, consider these to be sort of like jumping off points. So, even if the topic may not be anything that you're necessarily interested in, look at the abstract and see if there's any words that sort of jump out at you, and it's like, what is that? So it's a great educational tool, sort of self-educational tool. It's also, if you look at the bibliographies, right, the all the references, um, that is like a history lesson into that particular topic. So it's very awesome. They're a lot like the Supreme Court um, uh, opinions. They're great historical documents. It's absolutely amazing. They go all the way back to the beginning, so it's great. So if nothing else, treat these papers like that as sort of jumping off points into learning a little bit more. Maybe something will really grab you and you'll be like, oh, wow, that's really interesting. And I think I get it too. There's so much in astronomy, just incredible amount. Something for everybody, for sure. But not everybody. I don't think. I don't think it's fair to presume that everybody should be interested in science and astronomy. I don't think everybody has to be. Um, uh, no, I think you know whatever you're passionate about, do it. Right? There's lots of things I'm not interested in either. I think that was about it. That was about it with that. I wanted to maybe take a quick look over at Mars and see what's going on there. Call it uahirise.org. I guess it's the catalog we want anyway. But let's go here since it gave me the option to do that. Let's look at Mars for a little bit. Haven't looked at Mars in a little while. See if there's anything new. They, they did a big data dump. Maybe I want to say the 1st of June. Yeah, 1st of June. So yeah, they've dumped a couple others. So I don't know if you folks heard about this, heard this story. Everybody was really excited because they found a blue dune, and I guess it turns out that it was just the color that the person chose, um, and it has nothing to do with the actual color. So oh well. I think that was probably it right there. Dunes. Yeah, that's sand dune. Some kind of small particles, I guess, driven by wind. Something else. Don't know. But yeah, they colored this thing blue, and then everybody thought, oh man, they found a blue dune on Mars. Like no, no, not really. Bang and whoosh. Hmm, that's an odd looking picture. Wow. So what do you make of that? That's a little weird. That's a little weird. Yeah, I gotta say that's a little weird. I don't know about that one. Huh. Look around here, see if there's anything else interesting. That's a little weird, gotta say. Huh. I heard something about them thinking that this was some kind of avalanche, right? That a meteor hit here and caused this avalanche to come down like that. But I don't know. You got something going on here. Looks like an impact, but I don't really get that. It's a little strange. A little strange. Very awesome, though. Lingering, lingering frost. Ooh, this is a big one. Beautiful. Wow. Looks like plowed fields. That's pretty interesting. Wow, look at that. Huh. That's amazing. Pretty amazing. Mars is a pretty amazing place, but so is everywhere else, you know? New crater blue. Somebody was really into blue over there, making everything blue. Okay, so it looks like there's like a double, yeah, there's some kind of double impact here. Kind of cool. I haven't found any of those dust devil trails yet, and I really would like to find one of those because I've seen some incredible ones. The hills in Ganges Chasma. I haven't been able to find any. I'm not seeing any here, although this is just incredible. Look at that. Wow. Again, I always like to imagine standing there looking at this. Because these are on human scales here, right? I mean, every pixel is I think like 40 centimeters, 50 centimeters. So I mean, all of these things are on human scales. Just amazing, though. Look at that. Ice block avalanche. Yeah, so 31.9 centimeters per pixel. That's about a foot per pixel for you Americans that can't handle anything else but feet and inches. That even has a really funky surface to it. Yeah, pretty amazing. All right. Well, I think that we should probably just call it for what it is. And what it is it is time. It is yeah. I'm getting the call. So yeah, I think I better split for now. So hope everybody has a great evening, a great day tomorrow. Hit the thumbs up if you like this. Spread the word. Spread the word. Um, as soon as the funds appear in my PayPal account, I'm going to be getting a new camera. So that's to sort of celebrate having over 100 subscribers now. Number of subscribers doesn't mean much. What matters most is views, and probably even more importantly, the number of minutes viewed. Um, so yeah, make sure to share this around. I'm trying to find our core group, and yeah, it's going to be a pretty big number because this is a worldwide audience. So things are going well. Hope everything is well in your arena, and yeah, I think that'll be it for tonight, or today, or this afternoon, wherever you may be. All right, so take care, everybody, and I will see you on the spin tomorrow. Okay, uh, don't get dizzy or anything because it's a smooth ride. It's a pretty smooth ride. So all right, take care, everybody. I will see you tomorrow, 2 hours UTC. Bye.